Okay, any questions on that exam? Thank you. Have a nice day. Any questions on that exam? Okay. Here's another. Here, my ring is in the integers. My set of denominators, if you will. I noticed, by the way, this is an integral domain. My set of denominators with power of 3. So this is a subset of rational numbers that can be written like this. This is a ring, of course, because when you multiply two fractions, whose denominator is power 3, what do you get? You get a new fraction. Whose denominator is power? And how do you add two fractions that have a denominator power 3? Well, you get a new denominator that's also power 3. So this is both by that. Notice this one is strictly contained in the rational numbers because, for example, 1/2 is not in this one. Here's another example. I'm going to do R, C, S, set of odd, and so. This is a bigger ring. This is a subring of Q. This is also contained in Q strictly. Again, in this ring, there is no 1/2, right? But this one's bigger than that, right? Because the denominators here can only be powers of 3. The denominators here can be any odd number. It can be 11, it can be 33, whatever you want. By the way, so I want to bring up some illustrative examples here. Both of these sets, odd integers, powers of 3, they're both multiplicatively closed. And they're also saturated. All right? Anybody remember what is true about a set that is both multiplicatively closed and saturated? You're close. Its complement is a union of primes, right? Here, the complement of the odd integers should be a union of primes. And in fact, this one's fairly easy. What is the complement of the odd integers? The even integers, which in fact is the prime ideal. You see, everybody agree with that? This one's a little bit harder to see. What's the complement of this? Yeah, how do you rate the powers to be? Well, the complement of that, everything that's not a power of three is what? The complement of this is, well, 0, I guess plus or minus 2. Oh yeah. 0, yeah, that's true. So what is the complement? We've got, in this complement, we've got 0, we've got 2, not 3, we've got 4, 5, 6, 7, and also negatives. Can anybody see this as union front? This is the complement of this, everything that's not a power of 3 is in some prime ideal that is not the ideal term of 3, right? So for example, what's not in, well, 0 is in every one of these, right? 2, that's in the ideal germ by 2. What else? 4, that's in the ideal germ. 5, that's in the ideal germ by 5. 6, that's in the ideal germ by 2, right? It is in 3, but it's also in 2, right? So this, but 9 is not in both 3 and 2. So that's the complements there. Any questions on this? Here's another example. So I'm going to leave this one for an exercise. See if you can work through this. How about one will 0 values? Um, you can check. This is actually well, I've got my mouse. That's a multiplicable closed set. One component's in there. 5 times 5 is 1. 5 times 3 is 3. So you can check. 3 times 3 is 3. See if you can figure out by writing down what the or fractions are. See if you can find R localized S. See, that's the complement of the ideal group 2. This should be a small C3, I guess. See if you can figure that out. Okay. Let me give you some sample notation. For example, I have a definition, if you will. Let R be an integral domain. Good. Then R minus E. Notice R minus 0 is the complement of the ideal 0. So this is automatically a saturated set. We'll prove that in homework. But if R is an integral domain, then the product of two non-zero elements is non-zero, which makes this a multiplicable closed set as well. So, and also, if R is an integral domain, zero is a prime ideal, and this is the complement of the prime ideal. This is a saturated multiplicable closed set. This S, and again, it's important that we have integral domain. R localized to S is called quotient field. So the quotient field is field, it's actually the quotient field of an integral domain is the smallest field that contains that domain. Right? It's a set of all fractions. And let me kind of show you why this is true. In this situation, if this fraction is not zero, the numerator can't be zero, right? Therefore, R is in R minus zero, which is S. So S over R is in RS as well. And RS. So for example, quotient field of Z is Q. The quotient field of any of you ever seen number theory or looked at this? This is called Gaussian integers. So it's sort of like complex numbers, instead of both integers being free to be any real number I want, they can only be integers. Right? Anybody want to guess what the quotient field of this is?
Only Q by?
That's a great guess. And actually, if you have here A, B, and X, Y are integers, see, this is going to give you a blast from the past. Do you remember when you were in algebra in high school and everybody's like, rationalize the denominator? Remember doing all that crap?
Yep.
Well, here we go. So if I do this, the bottom here comes, and of course I'm assuming here that this is not zero. This becomes x squared plus y squared on the bottom, which is just an ordinary integer, right? And it's not zero because this is not zero. And in the top I get ax plus by plus I times dx minus ay. And this can be written as ax plus by over x squared plus y squared. And this is I times dx minus ay over x squared plus y squared. And both these entries are in field. So the quotient field is as predicted by rational number plus I times one. Everybody up to? Here's something that you studied in calculus. I mean, not for its own, but I mean, you looked at a lot of polynomials, two derivatives, multiply them, they're continuous, they're great. Now, look at Rx. That is actually an integral domain. That's a consequence of what you got on the homework display. What are you supposed to quotient field with this is? The answer is not so hard as you might think. It's often written around bracket X. This is just P of X over Q of X, where P of X and Q of X are polynomials. This is just a quotient of two polynomials, as long as Q of X is not the zero polynomial. Anybody remember what this collection of functions was called? The answer was certainly rational, the notation that is. Anybody ever heard of rational functions? And they define that in calculus, rational functions for exposures to polynomials. Continuing with my example definition, this is a really, I got to apologize for this beforehand. This is the notation that is used in the discipline. If R is a ring and commutative and P in R prime, then actually I'm going to get more and P is a prime ideal, then S is a saturated multi-frequently closed set. Okay, we know something more general. We know that if you have in fact a union of primes, then R minus that union of primes is saturated multiple set. But in the special case where it's just one prime, so S is the complement of a single prime, then RS, which is the set of R over S, where S is not in P, is often written R sub B. And I'm sorry, that's awful, right? Because this is the notation is bad, but it's what's there to work with. So let me make the distinction. R over F, RS set R over S, S here, S is a multiple set if P prime ideal, then so when the substructure here, when the S is a multiplicably closed set, then the denominators come from that set. When this is an ideal, that means the denominators come from the complement of the ideal. It's a sucky notation, but that's what it is. And this is often called localization of this prime of R at the prime P. Okay. Definitely. This is another unfortunate. They didn't think the definitions out, but we did them. But on the if R has a unique max one then R quasi. So the term quasi-local means it's got one and only one max one ideal. If R has only finitely many max one ideals, R is called semiquasilocal. So you might wonder what the quasi is about. Is there such thing as a local ring? In the literature, so the difference here is my definition is an accepted definition is in the general sense. A ring has a unique maximum ideal, then it's called quasi-local. If it's only got finitely many maximum ideals, it's called semi-quasi-local. The quasi is removed if the ring is also in the theory. So what it means to say a ring is local is it means that it's got a unique maximum ideal and every ideal is finitely generated. So they remove the quasi if it's in the theory. If it's got finitely many maximum ideals and it's in theory, so it's got finitely many maximum ideals and every ideal is finitely generated, it's called semi-local. So anyway, that's the terminology. Here is an example. You can always construct quasi-local rings quite easily. Okay. Yep. R is you need to bring one and R prime. Yeah. Then R localized to P is always quasi-local. Let me give you kind of let me sketch this out, and the details that I skim over here will be made clear in the next theorem, or clearer anyway. So this, so R plus P are fractions. Numerator, anything in R, denominator, something not in P. Let me introduce you to a notation. If I in R is an ideal, then this notation I think is suggested. IS is the set of fractions where the numerator comes from I and the denominator comes from S, very much like we do with the ring here. So alternatively, IP would be alpha over S, alpha and I S dot D. That's how the notation works. Let me point out that this construction gives you actually a maximal ideal of R plus P. It's a set of fractions x over s, where x is the numerator is now from P and the denominator is not. Notice that nothing in here is invertible, right? Because for this to be invertible, then that would mean the denominator x would have to be not in P, which would be a direct contradiction. So these are all non-units. And it's pretty easy to check that because of the fact P is an ideal, this is actually an ideal as well. It's maximal because if you put any other fraction into this ideal, it necessarily has to be something whose denominator is, whose numerator is not in P, and therefore is a unit. So it's fairly clear this is maximal ideal. What is probably not quite as clear as 5 is the same one. Any ideal that contains this has to necessarily have a fraction whose numerator is not in P and is therefore a unit. The real question is, why is this the only maximal ideal? And here's a theorem that I will sketch a proof of. But this is the big theorem about localizations that we're going to do. And here we'll say that R is a community ring of 1. You can generalize the statement, but at this point, I don't care. We'll just do it for computer rings with identity. Then there's a one-to-one correspondence between the prime ideals of R that miss S and the prime ideals of R localized to S. Then there exists one-to-one correspondence between prime ideals. And I'm going to put this of R that miss S, that is P intersect S. Remember this notion of ideals missing multiplicative sets is quite important to solve for. Any ideal is maximal with respect to missing multiplicative sets prime. And prime ideals are localized. And I'll show you how the correspondence works. So the prime ideals of the localization are localized with S correspond exactly with prime ideals of R that miss your set of denominators. Primes of R, say P, such that P intersect S is empty. This corresponds with primes of R localized at S. Start with the prime here and go to the prime here. Remember, this is set. E. So let me sketch a couple of things about this here. Well, before I stand the I'll attempt to show some of this stuff in questions. Okay, so this is kind of an important thing. More generally than just primes, ideals correspond this way. Notice if I in R is ideal, then I sub S, which is alpha of S, in RS is ideal. Notice this is a non-empty set because, for example, 0 is in I, so you get the 0 element up here. This is a subgroup because you have alpha over S plus alpha prime over S prime. This is and notice this is in S and this is in I because I is an ideal. All right, so hitting this by alpha, that's set into I. So okay, good. This IS has got to be a subgroup. Also, this is in S and this is in I. So it's an ideal as well because it's such stepped in because of the fact that the numerator is where you. Let me point out also here, P is prime, so is PS. Let me prove that real quick. Well, actually, let's start by assuming that P is prime. And R over S times R prime over X prime is in P localized at S. So that means R prime over S prime is P over S double prime, where P is P and S double prime S. here, well, S and S prime S. What does it mean for these two fractions to be equal? T times the cross multiple thing times P S prime is equal to 0. Everybody agree with that? And what does this mean? Well, this means that R prime S double prime P is equal to P S prime. This thing is in P, right? Because P is. So R prime P. The product of these four things is in T. So one of them has to be in P. One of them has to be in P, but it can't be T and it can't be S double prime. Why? Where do S double prime and T come from? They come from S, and P misses S, right? The intersection is 0. So S double prime P not in P. So R or R prime is in P. So R over S or R prime over S prime is in PS. That proves the one direction, and we need to quit for today, but we will pick this up next time. Any questions? Okay, well, I will see you folks on Friday. All right.